class recording has commenced. So, yesterday, we started in on the last outline for this unit dealing with the origins of the universe, or one theory about the origin of the universe. And that theory started with the Doppler effect. The Doppler effect is not something that is exclusive to this theory. We've talked about the Doppler effect before. The Doppler effect being that motion will cause a change in the way that waves are perceived. We think of it mostly as sound waves, because that's kind of the waves that we deal with, and we can hear those, or we can hear the differences most easily with sound. But it works with any kind of waves, including light waves. And we said that as we look at the light that's coming to us from distant galaxies and distant stars, if those stars and galaxies are coming towards us, we perceive that light to have what we call a blue shift. That knowing what a galaxy is made out of and how big it is, and we can kind of tell what it's supposed to be made out of, we should see a characteristic amount or wavelength of light that comes off of it. Remember, when you look at this shirt and that shirt and that shirt and that shirt, we can tell they're different because they give off different light. Does that sound familiar? So different galaxies give off different kinds of light. And we have an idea of what that light should look like. And when we actually get it, though, it doesn't look like we think it should look, based on the fact that it's moving. So we have some that show blue shift and some that show a red shift. And from that, we can either tell whether objects are moving towards us or moving away from us. Okay? Are we okay with that? Okay. So now, let's take it from there, because that's where we left off yesterday, right? So, in the early, or actually late 1920s, an American scientist named Edwin Hubble starts looking at the light that's coming from other galaxies and making precise measurements, and realizes that most of the light that we receive here on Earth is undergoing a red shift. And we said that a red shift is indicative of what? Like things that are making that light moving away from us. So he goes, all right, well, if everything's moving away from us, then that must mean, or if everything's got a red shift, that must mean that everything is moving away from us. But there are other things that go along with it. For example, sorry, did everybody get that part?
Yes.
All right. So if I take this circle, okay, and I expand it out, like that, okay? And then, actually here, let's do this. Okay. Circle, okay, and another circle, okay, like that. And I'll try and make these so that they're all, does that look like they're all kind of together?
No.
Kind of, sort of?
Sure. What? No.
Are they concentric? And here's Earth. Okay? So, let's group these all together. Okay? And, okay. So, this is one model of the expanding universe. So we start here like this. Okay? And here's Earth. And so there's some star over here, and it's giving off light towards Earth. Okay? And then there's some star over here, and it's giving off light towards Earth. Okay? And if everybody is where they're supposed to be, everybody is still, this light looks yellow and this light looks orange, and it's great. Okay? But if I take this and I expand it out, like this, okay? This yellow star is moving out towards the edge of the board, right? Okay. And we're moving out towards the edge of the board, so this star is moving away from us, right? Okay. Hubble sees a red shift. But how's this star moving?
Towards us.
It's actually moving towards us. So we would see a blue shift out of that star. But that's not what we see. Almost every star is showing red shift. So is this what the universe looks like? No. The only way that every star is going to show a red shift is if we ungroup these. Okay? This ring, I gotta ungroup these too. This ring is getting bigger. Okay? And this ring is getting bigger. But not as fast as the outside ring is getting bigger. The outside stuff is moving faster than the inside stuff. And the middle one is getting bigger, but not quite as big or not quite as fast as the inside one. So this yellow star would be moving away from us because the outside part is moving faster than the middle. But we would also be moving away from the orange one because the middle is getting bigger faster than the orange. Does that make sense? So the universe is expanding, but it's not all expanding at the same rate. That galaxies farther away from Earth are showing a greater red shift, meaning they are moving away faster. They're moving away from us faster. And Hubble goes, the only way that happens is if the universe is getting bigger. The universe is expanding. And as it expands, it's actually gaining speed. Good there? As tricky as that is, we understand. Okay. So, where does that lead us? That leads us to, all right, if galaxies are all moving away from us, yes, go ahead.
Would that mean there's no gravity out there?
No.
When you did the demonstration yesterday, didn't they say the same length away?
Yes, if gravity was acting on all of them equally.
Okay.
But that means that gravity isn't acting on all of them equally, and that's kind of an important part. Okay? Because gravity also depends on distance. And those galaxies that are farther away, they don't experience as much gravity as galaxies that are closer to the middle. Okay? All right. Working backwards, if galaxies are all moving away from us, it would suggest that at one time they were all in the same place. By measuring how fast those galaxies are moving, you can figure that out if you know the red shift. And calculating by knowing how fast they've been moving, it's been calculated, and knowing how far apart they are, you can work backwards and say, seems like these things have been going for approximately 14 billion years ago, right? As the song so eloquently states. Okay. Good there? So, that leads us to the Big Bang Theory. Astronomers theorize, right, come up with an explanation that the universe came into existence in a single moment known as the Big Bang. That at one time, all of the matter and energy in the universe was concentrated at a single point. Is it as big as that point on the board? I don't know. Nobody really knows. Okay. Now, if you've been paying attention for a while, you might have a problem with that. Anybody got a problem with that?
Because they're all trying to stand out or get they're trying to repel the light.
Okay, so we got a problem there, right? Even if we try to put two protons in this space, are they going to like being there? No. What else?
I was just going to say, because like matter can't occupy the same space.
Can I fit all of the matter that's on Earth into this space? No. But what did Einstein tell us about matter? Matter could be in the form of energy, right? Is it okay if we have all the energy in the universe in this space? Yeah, that's okay, right? That whole superposition principle, blah, 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 blah. So, we see ideas reinforcing one another, right? But if you've got all of the energy in the universe in one spot, how hot do you think that is? Pretty hot, right? Okay. So, doesn't like that. So what happens? Boom. Okay. Because hot things have a tendency to do what? Expand. But what happens when hot things start expanding? They do that, but what happens to them as those hot things expand? What generally happens to them? Pressure decreases. What happens to their temperature? They cool down. So as hot things expand, they tend to cool down. Okay. The universe begins to expand and cool. Guess what? If energy cools down, what can we make now? Now we can start making matter. Okay? If we get through all this, maybe.
Okay, go.
So, this energy begins to cool down, right? After a while, right? Soon, now we're still talking like hundreds and thousands of years, okay? The temperature's cooled enough to start forming atoms. But atoms don't form right away. First, things like protons and electrons form. But even if protons and electrons still have a lot of energy, do they like being together? No. You got to cool it down a little bit more and lose a little bit more energy. And then you can start forming things like atoms. Once you form things like atoms, now you can start forming things like molecules, and then you start forming things like people and whatever, right? Okay? Obviously not right away, okay? But that's what we get to. All right. Once you've expanded all that stuff out, it's cooled down, it's turned into matter. Now matter starts getting affected by gravity, and gravity starts coming together and pulls things into nebula, and then nebulas begin to form stars, and blah, 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 blah. Okay? Good there? As it keeps going, the universe continues to expand, continues to cool down, more stars form, and you start getting things like planets, etc., 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 etc. What?
We don't have the exciting ones.
Oh, I know. That's fine. So the allotropes begin, and eventually you get a wall and a pyramid. So. All right, good there. True. So, did it happen? Okay. Well, we have some evidence to suggest that. Okay. Well, we already talked about the redshift, right? That all this evidence suggests that these galaxies are moving away from one another, and that which would suggest that at one time they were together. But we also have this stuff that we call cosmic microwave background radiation. There's just a bunch of energy that's floating out there in space. Where did it come from? It didn't come from anywhere. It's just there. Right? And we can detect that radiation without too much difficulty, and we can't really trace it back to anywhere. Well, where did it really come from? It's just there. It's left over from the Big Bang, right? Like when things explode, right, pieces go flying everywhere, but some stuff just, shoots out. There's a bunch of energy that's just left out there, just floating around. It didn't cool and form into atoms and molecules and stuff like that. It's just energy out there. Go ahead, Farah.
You would eventually cool and form matter.
I suppose it's possible, you know, although it's more likely that it goes in somewhere and gets absorbed by some matter that's already created, and that matter then increases in energy. That's probably more likely. You know, if it hasn't cooled and formed into mass at this point in time, it's probably not going to. Okay. All right. So, if that's what happened at the beginning, that leads us to the next question. What's the next question?
What's the ultimate fate of the universe?
What's going to happen at the end, right? If that's how it started, what happens at the end? Okay. The real key determining factor is how much mass is out there in the universe. Why would that be a key determining factor? Anybody? Why would the amount of mass that the universe contains play a key role in determining what happens to it at its end? Okay, was that a hand or was that a stretch?
Well, could it be because it depends on how, because it took longer if it had more mass, because it had to take longer to cool down and...
Okay, I'll give you that, although how does that then ultimately go towards the, how does that then ultimately fate the end?
Because then it, after the energy cools down, it turns into mass, or, matter, and...
I can see where you're going with that. Maddie, go ahead.
Matter can't be created, so obviously it's just going to stop.
Okay, there's that too, although it's not really where I want us to go. But that, those two are, okay, so did you have something that you wanted to throw out there? Never mind. Max, do you have something that you want?
It's like how the stars, pi, and all mass.
Okay. It has something to do with stars, kind of. Austin, right? Ultimately, what's going to slow this stuff down? Gravity. Gravity depends on what? Gravity depends on mass. So, how much mass the universe contains will ultimately determine how much gravity is there. So what are some options as far as what might happen? Katie, go ahead.
They'll come back together.
Ultimately, if there's enough gravity, right, just like this ball, if I throw this ball up in the air, right, what happens to it? Slows down, stops, and comes back to me. Is that any different than the universe? The universe being like the big, me throwing the ball, be like the big explosion, right? It shoots everything outward. But eventually, what might happen to that stuff? Slow down, stop, come back together. Okay? Okay, what else?
Wait, so, oh my gosh, does this mean that eventually, if after this universe comes back together, another one could be created, and after the human race is gone, there could be another?
No.
Is it possible?
Yeah.
Sure. Okay. Now, here's the weird thing.
That's, oh my gosh, that's really weird.
So,
That's like freaky. That's like parallel universe freaky. That's weird.
What if
So,
the universe all arranged itself?
Oh my
if the mass is large enough, just like me throwing this ball into the air, it slows down, stops, and comes back to me. If the mass of the universe is large enough, the Big Bang is like me throwing the ball up in the air. That stuff goes out, it eventually slows down and stops, and then it comes back together. Eventually it'll end up back where?
Where it started.
Where it started, in that nice little point of energy. Okay? Now, Katie.
But how does the matter like break down back into energy though?
If you, like say, in a star, what happens? How does a star get started, Becca?
Gravity pulls it together,
And
then
it starts doing what?
starts to like fuse, and then
Starts smashing stuff together, right? And if we smash it together hard enough, fusion starts. But we said one of the things that happens during fusion is some mass is converted into energy. If you smash them together hard enough, right, what's going to happen to the mass?
some of it's gonna turn to energy.
It's going to turn into energy, right? times did I throw the ball up and down?
3.
3. What if we're like on the up trip of the third explosion of the universe?
Oh my gosh.
Okay.
That means that.
But here's the weird thing. According to all of our data and all of the estimation measurements that we've taken, our perception of time began at the point of the Big Bang. So there's no way, at least that we know now, for us to ever know if this has happened.
Except for when we're reincarnated.
Possibly.
Yeah, we're on planet like
So,
the last.
yeah. Or maybe like in Futurama when they like chop their heads off and put them in the jar, you know. So. But anyway.
Well, it won't matter because then we'll all get squished together and all the energy.
Right. So we don't. I mean, like I said, all of our perception of time all began at the Big Bang. So we don't really know. There's nothing to suggest that, but if that's the ultimate fate of the universe, right? If it started off as a little ball of energy and exploded, and it goes out and stops and comes back to a little ball of energy, what do you think is going to happen again? Probably going to explode again, right? But the other option is, there's actually two other options. If there isn't enough mass, right, that universe would just keep continuing to expand continuously. And that's a weird thing to think about too. Because most of us would say, okay, well, if I wanted to do this, I would say, okay, let's take a balloon, right? And we blow a balloon up. And if I blow the balloon up more, it becomes bigger, right? But here's the problem with that analogy. If I did that in this room, what would eventually happen to my balloon? Well, in reality, yes. But let's say I have an indestructible balloon. And I just keep blowing it up and blowing it up and blowing it up. It fills up the room. But the problem is, there is no room. The universe isn't... Hold on. The universe isn't like a balloon in a room. The universe is the room. And there's nothing outside of it. What do you mean? It's like a vacuum? No. It doesn't exist. There's no trees, there's no school bus, nothing. Okay? So that's different. Well, how does it get bigger then? What does it get bigger into? It just gets bigger. The room gets bigger. Well, does that mean it goes into the next room? No, there is no next room. This room just keeps getting bigger and bigger and bigger and bigger. It doesn't take up that room. It doesn't take up the room down underneath us. None of that exists. So how does it get bigger? What does it get bigger into? Don't know. Just does. All right? Becca, does that help or hurt your question?
No, it's just like weird because like we don't. It's weird to think about because we don't know what's right, we don't know what's wrong, and we don't know why. It's
Right.
just like,
We have, Becca,
it might be this,
we
but
have,
it might be this.
going
it
back-
might be something we don't even know about. Like,
going back to like the first day, right? We have facts. The fact is the universe is expanding. We know that. That's a fact. It's a repeatable observation by multiple people. Second, we know that there's this cosmic background radiation that's out there. Fact, we know it. Fact, we know that energy and mass are two forms of the same thing, right? So then we, like I said, now we try to explain facts, right? With laws. Hubble's law says this, I see redshift, therefore the universe is expanding. It's not a why, it's just a what. The Big Bang Theory is a why. That's why it's a theory. You know what I'm saying? It explains why is the universe expanding. Well, it takes all those facts and says, well, there was a little ball of energy and exploded. You know? Does that make sense? But, like we said, our theory's always right. Sometimes we find evidence that says what we thought was the reason why something was happening isn't why it was happening. Does that make sense? So then you have to go back and revise your theory. This is totally theory. Well, this is actually more hypothesis, right? It's an educated guess, because we don't have any facts to suggest what will happen at the end of the universe. Okay? Benny, go ahead.
If we do have enough mass and it's large enough and the gravity eventually pull together, wouldn't we see all the red shift turn into blue shift?
Yeah, we would see the red shift turn into the blue shift then. Yeah. Right now, we don't see that.
Yeah.
Yeah. Sorry, go ahead.
That was my question.
That was your question. Wow, that's crazy. All right, go ahead.
So, if the fate of that the universe would just keep expanding, that would off of their estimated Big Bang?
Yeah, that there was so much energy at the beginning and not enough gravity that it just keeps going and going and going. There's a third option that it expands to a certain point, slows down, and then it just stops. It's like you know, if I wanted to roll this ball onto the table, right? One option is it stops before it gets to the edge. Second option is it rolls off the edge. The third option is I roll it just right and it stops, like right there. You know what I'm saying? Or if we were trying to roll something up the top of a ramp, right? You could either roll it not hard enough and it rolls back down, or you could roll it too hard and it rolls off the edge, or you can roll it just right, then it goes just like that. Okay? That's a third option. Now, so the ultimate fate is going to be determined by what? Mass. So the next question is, so how much mass is there? And the answer is, we don't know. Because we can only see things in two situations, right? What's the only way we can see stuff? It gives off light or it reflects light. But there's a bunch of stuff out there, or at least we think there's a bunch of stuff out there, that is called dark matter. Why do you think it's called dark matter? Because you can't see it, which means it doesn't give off light of its own or reflect any light that goes off of it. Well, then how much dark matter is there? We don't know. We can't see it.
How do we know if dark matter exists?
We have evidence to suggest that it does. Like, if you look at things like black holes, we know a black hole is there because gravitationally we see things happening to it. But we don't know how big it is, right? So Nicole, I used this example earlier. Let's say we were in a completely black room, totally dark, but this baseball was a glow-in-the-dark baseball, okay? If I threw the glow-in-the-dark baseball across the room, okay, and then on the other side of the room there's a ninja dressed in all black. First it was just a guy in a black suit, but the other class decided he had to be a ninja. Okay? And the ninja catches the ball. Okay? What would you see?
It just disappears.
You would see the ball do what? You would see the ball stop. Slow down and then stop. But do you know anything about the ninja that caught it? No. Well, yeah. Well, what kind of a ninja is he? How big is he? Is there more than one ninja over there and one of them just caught it? What? Chemical reactions occur that give off light. Okay? So, how do we know? We don't know. Okay? But we can look at things around it and figure out, looks like there's about this much there. But the real moral of this story is we have no idea how much dark matter is out there. Some people estimate that maybe 85% of the mass that exists in the universe is dark matter. But how much? We don't know. So it's really hard for us to detect it.
Quick, Big Bang sound, go.
Guess what? Black holes form from the star that exploded, and the mass gets squished down, and it's so great that the gravity is so strong.